Hello, class. This is a continuation of a lesson sequence on stoichiometry. In the last lesson, we discussed empirical formulas using percentages and converting them to masses, followed by converting our masses to moles, and then dividing by the smallest amount to get our whole number ratio for our empirical formula. There are two other ways we can look at empirical formulas. In this lesson, we'll look at combustion analysis and hydrates, which are a specific compound type we'll discuss. So combustion analysis can be used to identify empirical and molecular formulas for compounds that primarily contain carbon and hydrogen. When a combustion reaction of a hydrocarbon occurs, we know that the other reactant is oxygen gas because that's what fire needs to burn, and so that's how the hydrocarbon combusts. And we know that CO2 and water are always formed as products. In combustion analysis, you typically will be given the masses of your CO2 and the masses of your water and the original mass of your hydrocarbon sample. This can be used to determine the moles of carbon and hydrogen in the original sample, and if we know the moles of carbon and hydrogen, we can then perform our empirical formula process to determine the subscripts. So one thing to keep in mind is that there is one carbon atom or 1 mole of carbon for every 1 mole of CO2, and there is also 2 moles of hydrogen for every 1 mole of water. So you need to use your subscripts of carbon and hydrogen in those chemical formulas as mole ratio conversions. If a third element is present in the compound, its mass can be determined by subtracting the measured masses of carbon and hydrogen from the original sample mass. So we're going to take a look at that in our first example here. So this first example says isopropyl alcohol sold as rubbing alcohol is composed of C, H, and O. Combustion of 0.255 grams of isopropyl alcohol produces 0.561 grams of CO2 and 0.306 grams of H2O. Determine the empirical formula of isopropyl alcohol. Okay, so first thing we need to do is think about our chemical equation. We have, for our combustion reaction, C sub X, H sub Y, and then we are told there's oxygen in here. So oxygen sub Z. Oops. Plus, we don't know how many moles of that we have in our balance equation, but we do know that we have some amount of oxygen being burned, and we get some amount of CO2 plus some amount of water. Now, anytime you are given grams of a substance, you should just get in the habit of trying to get those grams to moles because that will be the most helpful for us down the line. So we have our 0.561 grams of CO2. If you want to cancel grams out, you're going to need the molar mass of carbon on the bottom and 1 mole of molar mass of carbon, sorry. The molar mass of carbon dioxide on the bottom and 1 mole of carbon dioxide on the top. So you've got 12.01 grams for the single carbon in CO2 plus 16 times 2 for your 2 oxygens. So the molar mass of carbon is 44.01 grams per mole. Actually, I don't need grams per mole. It's just grams with 1 mole on top. All right. So if we get that to moles and we repeat the same process for water, we're going to be able to figure out how many moles of your CO2 are also how many moles of your carbon. So since there's 1 mole of carbon for every 1 mole of CO2, you can use this mole ratio, 1 mole of C over 1 mole of CO2. If we check our units, grams will cancel, moles of CO2 will cancel, and now we're in moles of C. Now, we're going to need the moles of C when we are doing our empirical formula, but we also need the grams of C, because what we need to do is figure out how many moles and grams of oxygen we have in our compound. So I'm going to go through and at least get this part, 0.561 divided by 44.01, and then times 1 over 1 is the same. So I'm going to try not to round here. I know on paper when I write it, it's going to look like I'm rounding, but I'm just going to put that number here for a second. Moles of C that we have is 0.0127 5, I guess, for now, moles of C. And I'm just going to save that number. And then I'm going to convert this to grams, because I'm going to need those grams to figure out my oxygen in a little bit. I know I've got 12.01 grams of carbon, which is what I want. That's my molar mass, over 1 mole of carbon. And that way the moles of carbon cancel. So I can multiply times 12.01. And what I have done here is, in my original sample of the 0.255 grams of isopropyl alcohol, I have determined that of that original sample, 0.153 grams of it is carbon. Okay. Now, I know this is true because of the law of conservation of mass. If the only source of carbon and hydrogen comes from the isopropyl alcohol, then all of that carbon and hydrogen must be in the products of CO2 and H2O. So the mass of carbon that's present here must also be present here. Same idea goes with hydrogen. The mass of hydrogen present here must also be present here. What's tricky about oxygen is that oxygen's split up into 2 different locations on each side of the reaction. So I'll show you how we can find that in a minute. So I'm going to go through and repeat this process again with water. So with water, I've got 0.306 grams of H2O. We got 1 mole of H2O on top, and then the molar mass of H2O on the bottom. We've got 16 grams for oxygen plus 2.02 grams for hydrogen, since there's 2 of them, each one of them being 1.01 grams. All right, and now same process, I need that mole ratio. So for every 1 mole of H2O, I have 2 moles of H. So this one is tricky because I'm actually going to need to multiply this by 2. So 0.306 divided by 18.02, and then I'm going to multiply that by 2 over 1, which is just multiplying by 2. And again, I'm going to, off to the side here, maybe I'll put it on the bottom. Oxygen, we're going to have 0.03396 moles of oxygen. And we're going to need to save both of those numbers for later because of our empirical formula calculations. And I'm sorry, I said oxygen. I meant hydrogen. My bad. This is how many moles of hydrogen we have. So we check our units, grams of H2O cancel, mole of H2O cancels. So then our last part is just figuring out our 1 mole of H is equal to 1.01 grams of H. Now I need this because, again, I'm going to still need to find out how many grams of oxygen are in my original formula. So I'm going to multiply, oops, move that out of the way, multiply by 1.01, and very similar number in grams, but I get 0.0343 grams of H. Okay. Now, in order to figure out the amount of oxygen, I have my original mass of my hydrocarbon, so 0.255 grams. If I know the mass of my carbon and the mass of my hydrogen, then the remainder has to be the mass of oxygen. So I'll subtract these out. So 0.255 minus 0.153 minus 0.0343. And I get the mass of oxygen as 0.0677 grams of oxygen. Now, you guessed it, if we have grams of oxygen, we now need to get this to moles. Now, I'll be honest, I did not leave enough space on this, so after I do these conversions, I'm going to have to clear this, and I'm going to have to set up the actual empirical formula calculation. All right. So then let's see, we're going to convert our grams to moles. So this divided by 16 grams for your oxygen, and we end up with 0.00423 moles of oxygen. All right. So what I'm going to do is I'm going to go through and erase these parts here, because I no longer need the grams, but what I do need are my moles. So what's interesting about this particular problem setup that we have here is that we didn't have to do percent to mass. We didn't have to do, well, we did have to do mass to mole in a way, but it's not in the traditional sense. But now that we have each of our components, we can now divide by the smallest amount. So this is a different approach depending on if you've got combustion analysis results here. This is a 0, I apologize. 3,396 moles of H. And then for oxygen, I've got 0.00423 moles of oxygen. Okay. And if I divide by the smallest, it looks like I'm dividing by my oxygen, 0.00423 moles. And we do that for each one. Okay. And this one obviously gives us 1 when we divide by ourselves, but 0.3396 divided by 0.423 gives us 8 for my hydrogen, of just about 8.02, and then for carbon, 0.01275 divided by 0.00423 that gives me about 3 for my carbons. So my empirical formula for my isopropyl alcohol is C3H8O. Okay, and that would be my final answer. So this is very similar to the process before, but we're not given percentages, we're given masses to start. And the masses that we're given aren't even the masses of our reactants, it's actually the masses of products. So we have to work backwards here to figure out our moles, and then once we can figure out our moles of everything, we can figure out our empirical formula from there. Okay, go ahead and try the next two problems down below here for you. Try it, set 8. Similar though, a couple things to point out. In number 1, they ask about the molecular formula as well. Same process we used in the last video. Once you have your empirical formula, find the molar mass of your empirical formula, and then the molar mass of the molecular formula divided by the molar mass of the empirical formula tells you how many times you need to multiply the subscripts by to get the molecular formula. All right, and then the last problem type that we're going to look at dealing with empirical formulas, and that will be it for this video because this one is going to be running long, I can tell already. The third type is determining empirical formulas of hydrates. So we're going to do one of these in the lab at some point. A hydrate is an inorganic salt, which is essentially just an ionic compound, metal and nonmetal. But what's interesting about the crystal structure of this solid is that it contains water molecules combined in a definite ratio. So when we write the chemical formulas, you write the ionic compound, and then we use a dot, and then the number of water molecules that are attached to that crystal structure as part of that unit. So for example, I have copper sulfate, CuSO4, and it is called copper sulfate pentahydrate because there's 5 water molecules attached. These are also sometimes referred to as waters of hydration. You do need to count these when you're doing your molar mass for a hydrate. If it's just the ionic compound, you find the molar mass of copper sulfate, which you can see here is 159.62 grams per mole. We find the molar mass of water, which we know is 18.02 grams per mole. But if you want to find the molar mass of copper sulfate pentahydrate, you'll have to multiply your water mass by 5, because that's the number in front. That's how many moles or how many molecules are attached. And you add that to your original copper sulfate value. So the molar mass of copper sulfate, the anhydrous type, is 159.62. The molar mass of copper sulfate pentahydrate, which is the hydrate version, is 249.72 grams per mole. So it's quite significant. We do need to count the mass of those waters. Now, anhydrous I mentioned briefly a minute ago, but that means without water. In the lab, what we're going to do is use the mass of a hydrate. We know that water, when it's heated above its boiling point, will evaporate. So we'll heat our sample of our hydrate. And as a result, the water will be driven out of the hydrate compound until it forms an anhydrate. So we measure the mass of our hydrate before heating, the mass of our anhydrate after heating, and then we can use that to determine the number of waters of hydration in the hydrate structure. So we'll do this example here. It says washing soda. Oops, didn't mean to do that. It says washing soda, a compound used to prepare hard water for washing laundry, is a hydrate, which means a certain number of water molecules are included in the solid structure. Its formula can be written as sodium carbonate X H2O, where X is the number of moles of H2O per mole of sodium carbonate. When a 2.558 gram sample of washing soda is heated at 125 degrees Celsius, all the waters of hydration are lost, leaving 0.948 grams of sodium carbonate. What is the value of X? This one's actually a lot easier than some of the other empirical formula problems we have. If all the water is driven off, what we can do is subtract here 2.558 grams of our hydrate minus 9.48 grams of our anhydrate. I'm going to use the vocab terms there. And what that will give us is the mass of water by subtracting those. So 2.558 minus 0.948. And that tells us that the mass of water that was driven off is 1.61 grams water driven off. And when I say driven off, that is the water that's lost due to heating. Now, the other thing to recognize is that I wrote anhydrate, but really this is our Na2CO3. So what we're going to do is convert both of those masses to moles, this one and this one. So 0.948 grams per mole of, or just grams, sorry, grams of sodium carbonate, and then 1 mole on top. And then sodium carbonate, we have to find its molar mass. Sodium is 22.99 times 2 plus 12.01 plus 16 times 3. 16 times 3 is 48. So we get a molar mass of 105.99 grams for our sodium carbonate, and then a mole of sodium carbonate up top. All right, and before I put that in the calculator, let's go ahead and set up the one for water. I've got my grams of H2O, my 18.02 grams of water on the bottom, my mole of water on top. Okay, and let's convert these. 0.948 divided by 105.99. So 0.00894424 moles of sodium carbonate. And I'm not going to clear the or cut those off yet because I want to use as close to exact numbers as possible. 1.61 divided by 18.02. So this tells me I have 0.089345172 moles of H2O. Now that we have moles of each, what we can do is figure out the number of waters by dividing the number of waters, or the moles of waters, by the moles of anhydrate. So really the key to solving this is mole of H2O over mole anhydrate. Is equal to the number of waters in the compound, in the hydrate. Number of H2O in the hydrate. Okay, so what we'll do is I will divide my moles of water by my moles of my my anhydrate, and you'll see it comes to 9.989, which is about as close to 10 as we can get. So I'm gonna make sure that I show the work here. 0.0894424 moles of Na2CO3, my anhydrate, and this gave us about 10, which is equal to X. So the actual formula for this is Na2CO3, the dot, and then 10 H2O. Okay. And that's really all there is to it. That's the same calculation you're going to end up doing in the lab. Go ahead and try this last problem in the You Try It set 9. Very similar setup, this time with a magnesium sulfate hydrate. And that is all for this video. See you in the next one.